Hi, this is Math 150, Chapter 6, Section 1, Radian Measures. So up until now, we've been working with angle measurements using degrees. We've talked about the alternatives and at least mentioned it, that your calculator has to be in degrees, not in radians. Well, now we're going to learn about what a radian is. So if we have a circle, right, we know that we can have an angle. We know there's 360 degrees in the circle, right? So there's a total of 360 degrees in the circle. We know the circumference of the circle is equal to 2 pi times r. So, in essence, 1 radian, let's see, if the angle theta intercepts the circle and creates an arc, right? What we're talking about here is this arc here that equals the radius. Then theta equals 1 radian. And it seems confusing, I understand it's going to get a little bit easier. But in some of the sciences, it's actually easier to work in radians than it is to work in degrees. So basically, if this is r, if that's the same as the radius, then theta is 1 radian. Well, since the circumference is equal to 2 pi of these r's, there are 2 pi radians in one circle. So 360 degrees equals 2 pi radians. And that's really the important thing to measure, or to keep in mind. We know that 180 degrees would be half of that, right? Just pi radians. And these are some relationships that you just remember and go from there. So, knowing that 180 degrees is equal to pi radians, right? If I divide by 180, what I get is 1 degree equals pi over 180 radians. So, if I had 45 degrees, well, for each of those degrees, I have pi over 180, right? So 45 goes into 80 4 times. So I have 45 degree angle is pi over 4 radians. Well, that would mean that 90 degrees is pi over 2 radians, because 180 is the whole pi, if you will. So if I take the circle, right, and I've got this, I've got 180 degrees. So if this is 90, if this is 30, if this is 45 degrees, and this is 60 degrees, and this is 90 degrees. This is pi over 2 radians because this is pi radians. So this 90 degrees is half of 180. 45 degrees is half of 90, so it's pi over 4 radians. What about 30 degrees and 60 degrees? Well, let's take the 30 degrees. Let's multiply that by pi over 180. Right? 30 goes into 180 6 times, so it's pi over 6 radians. And 60 degrees would be double that, right? So 60 degrees would be double pi over 6, which is just pi over 3. Well, 60 is 1/3 of 180, so that makes sense. Right, so if you turn to page 569, you'll see a circle that has a whole bunch of these angle to radian measures, because there's some that are more popular than others. You don't have to memorize 20 degrees or 15 degrees, but it does help if you remember 30, 45, 60, and 90, and from there you can kind of work backwards to figure anything out. Like, if I know 30 is pi over 6, then 10 degrees is 1/3 of that, or pi over 18. So you can kind of work between degrees and radians if you just remember a few of them. Now, what if I'm given, well, let's go back to this. 180 degrees equals pi radians. Well, what if I needed to figure out how many radians? Well, if I divide this side by pi, I get 1 radian equals 180 divided by pi. So if I gave you an angle measure, 9 pi over 4 radians, well, this is just 9 pi over 4 times 180 over pi. Right, and obviously the pi will cancel. 4 goes into 180 45 times. 45 times 9 is 405 degrees. So I can go between radians and degrees, degrees and radians, right? So that's going to be important and helpful. Now let's take a look at the circle again. If I had this angle theta, this is a radius, and S is the measure of some arc. So this measure of the arc, right, there's the length is what I'm really looking for. How do I find the length of an arc? Well, a lot of it depends on what the radius is. So if the radius is 5 centimeters and the angle is 3 pi over 8 radians, then S is equal to r theta, where theta has to be measured in radians and r is the radius of the circle. So S is equal to 5 centimeters times 3 pi over 8 radians. So S is equal to 15 pi over 8. So if I take 15 pi, 15 times 3.14, right, this is going to be equal to 47.1 divided by 8. S is equal to 5.8875 centimeters. Now there's something you have to know. When working with measurements, we always want to express the answer in the least number of significant digits. Sorry. So by least, we look at the measurements here, right? We have a measurement. We have 5 centimeters. 5 centimeters is 1 significant. So given the above, with r equal 5 centimeters, this is equal to 1 significant digit. The answer would be rounded to the 1 significant digit, so S would be 6 centimeters. If R was equal to 5.0 centimeters, well, then that is 2 significant digits. Then S would be, I would need 1, 2. So I would round the 8 to a 9, so it would be 5.9 centimeters. So we always have to be aware that the rules for measurements tell us to always round to the number of significant digits based on which measurement has the least number of significant digits. Now remember, rounding is really just about introducing error. If I were to say, what's the exact, well, then I would leave 15 pi over 8. Because that's exact. As soon as I try to multiply to calculate an approximate value of pi, I'm introducing error. Okay? So there's some examples. I'll do one more, and then I'll point you towards the examples. Let's take an example. Given a circle with radius equal to 5 centimeters. Let's use the same thing. 5.0 centimeters. And theta equal to 120 degrees. Find S. Find the arc that angle intersects. Well, in this case, we have to take the degree measurements, right? And if you go back up here, right, if I take the degrees, 45 degrees, and I multiply it by pi over 180, right? So 120 times pi over 180, well, 60 goes in here twice, and it goes in here thirds. 3 times, so I have 2 pi over 3 radians. So now I can do S equals R theta 5.0 centimeters times 2 pi over 3, which is equal to 10.0 pi over 3. So X, or S, I take 10.0, 10 times 3.14 divided by 3, and I get 10.46 repeating. But since we are 2 significant digits, right, 5.0 is 2 significant digits, so I really am going to round to the 10, right? So the arc is about 10 centimeters. You know how hard it is to measure a distance around a circle? Well, that's what we're doing. We're calculating what the distance around the circle is. All right, so if you read the examples, let's see, 4, 5, and 6 on pages 570 and 571. There's a couple of applications. They take this concept and actually put it to practical use. There's one more topic I want to cover for this section, and we'll be done. So finding the area of a sector. In other words, we have a circle, we have an angle, we have a radius. What's the area in this sector? Well, I mean, there's a lot of different ways that you could do it, and I'm sure that if you put your mind to it, you could probably figure this out without any formulas. So let's take a look at this. The area of a circle, the area of a whole circle, is pi r squared, right? But theta is only a portion of the circle. So if I take the area of the circle and I multiply it by what portion this is, right? So the sector is whatever the angle is over 2 pi, right? So if that's a 45-degree angle, right, then that's pi over 4. So this is a portion that I'm showing you. You take the angle. So, for example, if theta were 360 degrees or 2 pi radians, then this would be 2 pi over 2 pi, and it's the whole thing. So the area of a sector is equal to theta over 2 pi times pi r squared. Well, we see that we have pi that cancels. So the area of the sector is equal to 1/2, right? 2's on the bottom, theta r squared, or 1/2 r squared theta. So if theta were 180 degrees, that would be pi, right? So this portion right here would represent 1/2 of pi r squared. If this were 90 degrees, that would be pi over 2. So it would be 1/4 pi r squared, right? Because 90 degree would be 1/4 of the circle. So this is kind of the magic here. So let's take an example. Suppose we have this water irrigation, right? And it's 321 meters. And we're talking about 15 degrees. So these water irrigation systems, you don't really see them around here, but out west you see, because they have these massive fields and there's these trolleys that are really long and they're kind of arched, and they have sprinklers on them that, you know, dispense water, and they kind of move in a circle. So you can calculate your water usage based on, you know, the circle and the timers and all kinds of stuff. Well, 15 degrees, we have to find 15 degrees as a radian. So you take the 15 degrees, you multiply by pi over 180. 15 degrees, and 15 goes into 15 once, and it goes in here, so we have pi over 12 radians. So now the area of the sector is equal to 1/2 r squared theta. So it's 1/2 of 321 meters. We're going to square that, times pi over 12. So this would be Well, the denominator is going to be 24. And 321 squared so now 1,034 or 103,041 times pi divided by 24 is equal to 13,481,1975, and these are meters squared. Okay, but 321 is only 3 significant digits. So we're looking at these 3 significant digits. So the 8 rounds the 4 to a 5. But I can't just drop 2 zeros because it will affect the value, right? I can't just ignore those. I have to turn them to zeros. And I could put, if I put 0.0, that would indicate, right, if I were to do this, that would be wrong because that would indicate that I was accurate to 5 significant digits. So it's just 130 or 13,500 meters squared. Okay? That's the important thing, is make sure you pay attention to the number of significant digits, because working with measurements requires that you're accurate to the lowest number of significant digits in the problem from the start. 15 degrees and pi, those are not really measurements. We're talking about, length, those kinds of measurements. All right, well, there's homework, and you can be happy. We're getting close to the end. There's only a couple more assignments that'll be left, and we will be finished. Thanks for watching.